Let's now look at the important function of requirements management, that is, the processes which we go about to make sure we're managing the requirements properly. Requirements management is the process by which changes to requirements are managed throughout the system lifecycle. The requirements may also change over time. That may happen throughout the life of the system because the business may change, the environment will no doubt change over the life cycle of a system, and things like laws and regulations will change, but also there'll be technology changes. It's often the case that more than 50% of a system's requirements are modified before it's put into service. We therefore need to manage the requirements as we develop them. Because the requirements set is complicated, a requirements management tool is generally necessary to assist in the management of such a large number of requirements. It's almost impossible to have requirements traceability without implementing the requirements in some automated context. And so we employ a requirements management tool. The tool has a number of functions listed here. First, it needs to support elicitation and allow requirements engineers to capture requirements as they're gathered. Once the requirements are captured, the tool should allow readers to browse the requirement set, but also to retrieve specific requirements and to generate reports of subsets of requirements based on selected criteria. The tool should also support traceability, to support forward and backward traceability, to allow investigation of how a high-level requirement is achieved, as well as to identify the origin of any lower-level requirement. Requirements engineers need the support of the tool to generate good requirements, with appropriate spelling, punctuation, and use of glossary terms and template structures. Requirement sets also need to be delivered in a variety of formats, so it's important that the tool allows import and export of requirements in various formats such as word processing and spreadsheet format. The tool should also support change control and change impact assessment, as well as the functional allocation and functional to physical translation. And finally, it's important the tool doesn't enforce any particular requirements engineering process. So that's a brief overview of requirements management tools. Let's now look briefly at the tools that support requirements engineering, that is, requirements engineering tools. Now, there are a very large number of such tools that may assist in requirements engineering depending on the particular domain in which it's being done. There are context diagrams, functional flow block diagrams, the requirements breakdown structure, N2 diagrams, plus other tools including structured analysis, data flow diagrams, control flow diagrams, IDEF diagrams, behaviour diagrams, and many, many more such diagrams, each of which tends to be a particular tool used in a particular domain. Here we focus mostly for simplicity and for time on the two probably most important tools, the requirements breakdown structure, the RBS, and the functional flow block diagrams, the FFBDs. Here we call the requirements framework the requirements breakdown structure. Now, we said before that's also called the functional hierarchy, but we'll refer to it as the RBS. Now, the words are chosen very carefully to differentiate this structure from the well-known project management document called the work breakdown structure, or the WBS. The RBS is grouped logically, the WBS is structured physically into a group of physical work packages for the configuration items that need to be developed. At the end of preliminary design, the logical groupings of the RBS are therefore mapped or allocated into the physical groupings in the WBS. The principal benefit of the functional hierarchy is it provides a very useful framework within which we can develop the requirements and then later on trace them, and that process is often called requirements flowdown. The requirements are captured in a functional hierarchy. A hierarchy is a tree. In maths we call it a directed graph. And in that tree, branches flow from the mission statement at the top down to the lowest level needs and requirements, which are the leaves of the tree at the bottom. At each level, we stay at a level of abstraction that remains within our intuition. Since we can only hold in our working memory half a dozen concepts, the framework encourages us to start with the mission statement, within which there were 5 to 7 key concepts. Each of those concepts is fleshed out as a statement at the next level, leading to 5 to 7 goal statements, each of which contains 5 to 7 concepts. Now, each of those goal statements can be fleshed out again at the next level into objective statements, each of which has 5 to 7 concepts, and so on. And the process continues until we reach the leaves of the tree. If we look at this tree more formally then, we can see that the addition of a numbering system allows each level to be associated with the level above and below. There are some general rules for developing the RBS. First, the RBS is a hierarchical graph, so the level that's being illustrated should be such that the portion displayed should be visible on a single A4 sheet of paper at no less than 10-point font. The naming of the elements should be consistent, so that the keyword phrases are verb-based. The length of the keyword phrases should be consistent as well. Normally 3 or 4 words are sufficient. Each keyword phrase must be unique, since we need to flesh it out to be a unique requirement. And finally, the elements should be numbered with a hierarchical numbering system so that we can trace from parent to children and vice versa. Here's an example of an RBS, in this case for a domestic security alarm as part of our house. If we look across the 5 elements at the first level, we can see the major functions of the alarm: to deter, to detect, to classify, to report, and to provide a market-leading alarm. If we look at the next level, the RBS shows the functions that combine to form each parent function at the level above. As you can see from this diagram, the RBS is a powerful tool to illustrate the functionality to be provided by the system. The hierarchical representation of the requirements in the RBS can also be supported by another tool called the FFBD, the Functional Flow Block Diagram. The value of the FFBD is it also shows the flows between functions, not just the hierarchical description of the functions. The functional flow block diagrams, though, should also be displayed hierarchically. That is, they should be able to decompose each of the levels to the next level down. A single level of the FFBD has to be illustrated again on a single A4 sheet of paper at no less than 10-point font. The functions in the FFBD should also be numbered and named so that they're consistent with the RBS. Here's an example portion of a first draft of an FFBD, again for our domestic alarm example. The diagram shows an early draft as it might have been prepared, for example, in a workshop with stakeholders. Note that the functions have yet to be formally written and the numbering system has yet to be applied. It's often best to capture the functions informally and then formalise them than it is to try and capture them all in some formal template. Notice that the FFBDs are very good ways of capturing the operational scenarios from which the needs and requirements will be developed, and by simply looking at this diagram you should be able to see what it is the users want to do with the system as they're describing it. Unlike the RBS, which just shows logical relationships, the FFBD provides the requirements engineer with information about the sequencing of functions. For example, the resident evacuates after they've set alarms, as you can see in the first 2 functions. Alternatively, as you can see in the middle of the diagram, all forms of entry are equally possible. So the first 2 functions, setting the alarm and evacuating, are in series. The entry functions are shown in parallel. That makes it great assistance then to the requirements engineer to be able to identify the interfaces. We saw earlier that requirements can't be managed effectively without good requirements traceability. Traceability ensures that we know where the requirement came from, what requirements are related to it, and what requirements were derived from it. Good traceability therefore allows us to identify all requirements affected by a change, for example. Now broadly there are 2 types of traceability we mentioned before: forward traceability and backwards traceability. Now with our RBS we can see how these traceabilities apply to the requirements hierarchy. Forwards traceability gives us confidence that each requirement has been addressed in the design. Backwards traceability allows us to trace from each requirement back to at least one parent requirement. Through forward traceability, design decisions can be traced from any given system level requirement, a parent requirement, down to a detailed design decision, a child requirement. For each requirement, we must be able to find at least one child in the subordinate design documents. If there's more than one child, we must be able to identify all of them. Backwards traceability ensures that additional requirements that haven't been formally endorsed by the customer haven't crept in. We call that requirements creep. Any aspect of the system that therefore can't be traced back to a high-level requirement is likely to represent unnecessary work for which the customer is probably paying a premium but hasn't authorised. We call those requirements orphan requirements, and an orphan requirement is out of scope. Well, it's been a bit of a hard slog, but we've now covered all of the basics that we need to be able to look at the life cycle phases in more detail. In the next module, Ian will begin discussion of the acquisition phase by examining conceptual design. If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.